So this is our senior project video, distribution line multi-tool. My name is Michael Garcia, fourth year electrical engineering student with a specialty in power.
Hello everybody, name's Sukhdeep Singh, fourth year electrical engineering student.
Hi, my name's Drew Miller. I'm a fourth year electrical engineering student.
Hello, I'm Ritwik Keshavath, and I'm a fourth year computer engineering student.
So in this video, we're going to be talking a little bit about our senior project and what it does, and also giving a demonstration of it. So this is our distribution line multi-tool. What it does is it'll go on a power distribution line, similar to kind of what we have modeled here. And its goal is to measure the current going through this line, and it will also measure the temperature, the humidity, and any acceleration on the line. And then that data will be reported back to a centralized location. And the goal is to provide more data to power companies to help them make decisions about the state of their lines and if they need to shut down power or investigate anything. So the way that this works is we have two current transformers. This one here is used for sensing current, and that current is measured by a microcontroller. The microcontroller also handles the temperature and humidity and acceleration data. This current transformer here is used for powering everything, using some power electronics. And then there's also a battery backup that can power the system in the event of a power failure on the line.
Hello everybody, I'm going to give you a little overview on our testing setup. So basically we're using a step-down transformer to up the current so we can model distribution line currents. So 120 volt AC comes through here, through this breaker, and then to the transformer where it's stepped down to 2.3 volts. Because of this transformation, we're able to put out anywhere between 0 and around 1200 amps through this setup, which is useful for modeling distribution lines. We have added a couple safety features, including this breaker, which should trip in case of bad short circuits. This is our 400 amp load bank, just a steel bar. It's pretty nice because it can hold the heat and sustain 400 amps. This is our more variable load bank. It's 3 rods in series, but you can adjust them by moving these terminals, and it produces anywhere between 0 and around 200 amps.
So just a quick overview on the overall chassis design. This top clip pretty much holds the current sensing current transformer and the power-based current transformer. The 5-volt rail that the sensor electronics needs on this side clip is powered from the power electronics side, and the 5-volt rails channeled through this upper channel seen on the top clip. In order to mount onto a distribution line, there's a clamping mechanism where this screw essentially is threaded upwards, and it applies pressure to this little cutout. The overall chassis is made so that it's easy to install and take off a distribution line. And the side clips themselves, so this left one and this right one, both encompass the electronics and the sensors. This left one specifically has the electronic PCB and the batteries. This right one has the LTE SIM board, the sensor PCB, and the microcontroller, as well as all the other sensors.
Now I'll discuss the data collection software that this device uses to detect faults and other disturbances. The PCB which contains the sensors, is connected to a SIM module, which is driven by the microcontroller to send data via a TCP connection to a server here. This server is provided by Sorocom and allows to process data. And the way we do it is the device will continuously pull sensors and detect them for any sort of dangerous conditions. So for acceleration and for current and for humidity and for things like that, if they are above or below a certain threshold, which we deem as a dangerous value, it will set a flag. And upon sending the data on the server, you'll be able to see what kind of flags were detected, which were set by the system on sending this data. And we send data every 30 seconds, and the latest data collected by all the servers will be packed into a message which will appear on this server. And although this graph is empty right now, whenever data points come in, they will be printed out onto a graph, and there will be trend lines in between each set of data to see how humidity, temperature, and current can vary over time to decipher and understand trends depending on where the device will be implemented.
With this type of data collected from the current sensing, the temperature, the humidity, and the acceleration, it can allow for trend lines to be established at certain areas. For areas more prone to heat waves during the summer, where there's a lot of dry shrubbery, it can aid in the utilities creating tactics to help prevent fires, so some sort of fire mitigation. It can also help with load dispatching during specific seasons, especially in the summer when the demand for current is higher, and they can dispatch more current when needed. This type of data collection also allows for extraneous events or rare occurrences such as downed power lines. The accelerometer would help provide information, as well as the LTE connection in detecting where this power line went down. These open circuit conditions and these extremes can help establish different types of trends that can be pertinent to the utility, and what they do with that data and how they perceive it is something that can just aid with fire mitigation and other stuff. So now I'm gonna go ahead and give a live demonstration of the distribution line multi-tool. I'm gonna go ahead and flip this breaker, and right now it's connected to the flat bar. This flat bar should give us approximately 400 amps once it reaches a thermal equilibrium. Device itself is connected right here. I'm gonna go ahead and turn it on. Alright, so the device is running at the moment. With the software side, it should be sending data in about 30 seconds. And I'm going to go ahead and give this to you.
So as Michael said, in roughly around 20 seconds now, we should be getting a data point which represents the initial statistics recorded by the device. Okay, here we have our first data point. We can see that our humidity is 55.31%. We have a temperature value of 22.5%, an acceleration value of 9.1 meters per second squared, a current value of 502.46. There can be, although depending on how cold the line is, we might get more or less current. It's usually less. And we have our error flag at the bottom, which is a hexadecimal digit which represents which flags were set. In this case, 80, the upper digit being 8, represents the fact that the device was reset. Now, in the second point, you can see that the current has dropped down to 489.36. The error bit is 0, which means that the device has detected no errors or threshold exceeding. Temperature is constant as well as humidity between the two, and in another point we can see that the current is lower. I've auto scaled the value, so now we can see the current going down as well. It wasn't seen before. And anytime we see that the device detects an error, the error variable will change. In order to demonstrate what the device will do when there is no current in the line, we will flip the breaker to turn it off, which means that the device will switch over to battery power, and it should still be able to send data reflecting the fact that there is no more current. So if we were to wait 30 seconds, it should report that we get little to no current, and the error variable will represent that there was a fallen current. So here it is. The current value is 2.06. With calibration, we realize that the actual current value is within 20 amps, which is reasonably accurate for the range of this device, which can measure up to 3,700 amps. And the error variable is 8, and hex 8 represents the flag that I set, which is that there is too low of a current. And we see here the current is even lower, the flag is still set, and humidity and temperature and acceleration are still constant, as they should be, because they are not dependent on the current. And now if we were to flip it back on, the device will switch back over from battery power to being powered by the transformer, and we should be able to see that data here. Okay, as we can see here, the current has gone back up to 463.05, which is accurate because the breaker was reset. Humidity and temperature are constant, as well as acceleration. And although the error variable still says 8, it usually takes a cycle for that flag to reset, as all flags are set to 0 upon sending, and this flag represents the state of the device in the last 30 seconds. And since current was set in between, that's why that flag is still there. And as you can see here, the flag has been reset to 0, and the device is operating at optimal conditions.